Good day and welcome back to our third and final installment dealing with quadric surfaces. And through videos 1 and 2, we introduced the idea of how we can use this method of traces to sketch quadric surfaces. So we have all of the tools. Now it's really just about practicing and becoming quicker and efficient with these methods. And also, as mentioned at the end of the previous video, there is an online program that is free and extremely helpful. And that program is something called GeoGebra. So think geo for geometry, gebra for algebra. And if you search for this program, it's something that is freely available. You can use it on your smartphone, tablet, or whatever your computer or device of choice might be. And in this video, we will look at two more examples using this method of traces. So we'll first tackle the example given here. And recall, as we discussed in the previous video, what we really need to do is go through and find and classify 6 different things. The z equals 0, z equals k, y equals 0, y equals k, x equals 0, x equals k. And once we have found and classified all of these, we should be able to, look at some number of these traces to get a really good idea of what the surface is going to look like. So for z equals 0, if we look in our equation, if that z term is just not present, what we would have is, and I'm going to arrange the order slightly differently here, y squared over 4 minus x squared equals 1. And the question is, what type of conic section does this give us? The answer is a hyperbola. And if we remember back to this first video discussing hyperbolas, this is going to be a hyperbola on the z equals 0 plane. So that would be the xy plane. And because of the form here, it's going to open along the y-axis, and its y-intercepts are going to be plus or minus 2. So if we were to go ahead and sketch this, so it's a hyperbola opening along that y-axis, and it intersects the y-axis at plus or minus 2. And remember, we should always, label those positive intercepts. And I've put dashes, specifically to allow us to see kind of some depth in the picture. And similarly, when z is equal to k, we would have y squared over 4 minus x squared equals 1 plus k squared over 2, which is also a hyperbola. And remember, the key indication that we have a hyperbola is this minus sign separating those two squared terms. Furthermore, I'll note, because they are hyperbolas, we do not need to worry about any restrictions in k. So moving on and doing the same analysis in terms of y. When y is equal to 0, we see from above our equation becomes minus x squared minus z squared over 2 equals 1. And if this looks a little bit funny to you, I would agree. The reason being is that what we have on the left-hand side is always negative. It's at least not positive. And what's on the right-hand side is positive. So it's not possible for us to find any point that satisfies this equation. So here I'll just say nothing. And what we mean by nothing is just really no point satisfies this equation. So that's perfectly reasonable, and in a moment we'll see why that's the case in the surface that we come up with. Now if y is equal to k, we would have minus x squared minus z squared over 2 equals 1 minus k squared over 4. So remember, we're kind of doing two things at once. We're letting y be equal to k, and then we're moving that term over to the right. But anytime I see more negative signs than positive signs, I kind of want to take care of that. So I'm going to just multiply everything by -1. So we could write this as x squared plus z squared over 2 is equal to k squared over 4 minus 1. And now this becomes more familiar looking, at least in terms of our previous example. This is representing an ellipse. And note there is a restriction to worry about here, because recall this k squared minus 1, that needs to be, k squared over 4 minus 1, excuse me, needs to be positive. So k squared over 4 must be greater than 1, or k squared needs to be greater than 4. So that gives us the restriction that we have an ellipse as long as k is less than -2, or k is bigger than +2. And if we look at our trace that we've drawn here, the z equals 0 trace, we see that the y values really are corresponding to being larger than 2 or smaller than -2. So we're immediately seeing that information in our picture. Now, because the y equals 0 trace was nothing, I'm going to leave our picture as is for now. But once we get a little bit more in with the x's, we'll come back and we'll sketch a y equals trace as well. Okay, now lastly, moving on to our x's. If x is 0, we have y squared over 4 minus z squared over 2 is equal to 1. So in the x equals 0 plane, i.e. flat on the screen, we have a hyperbola, and because of its form, we see that it opens along the y-axis, where it has y-intercepts given by plus or minus 2. So graphically, it will look as follows. So it's open along the positive y-axis and the negative y-axis. And note, this is flat in our screen in that YZ plane, or the x equals 0 trace. Similarly, when x is equal to k, we have y squared over 4 minus z squared over 2 is 1 plus k squared, which is also a hyperbola. And this gives us a really good idea of what the surface is going to look like. But if we want to give it just a little bit more structure, we can also take care of one of these y equals k traces. So as long as k is larger than 2 or smaller than -2. So for example, if I wanted to maybe do the y equals 3 trace, it's going to be an ellipse that looks something like this. If it's y equals, let's say, -4, similarly here, we get an ellipse. And this is something that the book would more technically refer to as a hyperboloid. And it even would go further and call it a hyperboloid of 2 sheets, because it's made up of 2 parts, and all of the traces are either hyperbolas or ellipses. Okay, so we will look at one more example going through this process, but I once again just want to reiterate that this is not something that is really a natural or easy process. It's something that certainly requires practice. There are plenty of good examples to find in the suggested problems. Also to remember that there's this program called GeoGebra, which you could go to and sketch the surfaces to check your work. All right, so let's go ahead and work through the traces. So once again, we're just going to go through this process. We're going to find x equals 0, x equals k, y equals 0, y equals k, z equals 0, z equals k. And note there's no order that we have to go in, and I just randomly picked x equals 0 to begin with. So when x is equal to 0, we see from our equation that we would have z squared equals 2y squared. And this does not fit the form of one of the conic sections that we previously introduced, but note we could simplify this algebraically by taking square roots to write it as z equals plus or minus the square root of 2y. And that would represent two lines. One line corresponding to the plus, the second corresponding to the minus. And in the x equals 0 plane, so flat in our screen, we would have two lines intersecting at the origin. So for the positive value, it would look roughly something like this. And for the negative value, something along those lines. And moving on now, when x is equal to k, we would have z squared minus 2y squared, so I'm moving the y squared term to the left, equals k squared. And this would end up giving us a hyperbola. And once we have a better idea of what the surface looks like, I'll come back and hopefully try to explain where we can see that hyperbola. Okay, so similarly, when y is equal to 0, we have z squared is equal to x squared, which once again observed by taking square roots, this would be z is equal to plus or minus x. And I'm going to have a hard time drawing this in my picture, so I'm actually not going to include it, but once again, I can note later on where that would come into play. When y is equal to k, we would have z squared minus x squared is equal to 2k squared, which is a hyperbola. Now when z is equal to 0, we have x squared plus 2y squared equals 0 squared, or simply a 0. And note this once again, gosh, doesn't fit one of our forms directly. We might want to say an ellipse, but it's equal to 0. So what are the only possibilities for an x and a y that would solve this equation? And I agree. The only possibilities would be x is 0 and y is 0. So we get the point. X is 0, y is 0, and no, we already mentioned z was 0. So the z equals 0 trace, i.e. the xy plane, is that point of intersection we've already seen. Now when z is equal to k, we have x squared plus 2y squared is equal to k squared. And this is familiar. This is an ellipse. And note there's actually no restrictions on the k value here because the left-hand side is non-negative, as is the right-hand side. And let's kind of picture a few of these traces. So if z happened to be something positive, and I'm just going to randomly indicate a z equals k, our trace would be an ellipse. Similarly, if it was something down here which was negative, maybe minus 3, it's also an ellipse. And this is something that we would refer to as a cone. And this may be a bit different than you would expect as a cone in the sense that our Calculus 3 version is more of a double cone, opens upward and downward. Now in terms of seeing some of these other traces, I'll let you think about these lines z equals plus or minus x, but let's see these y equals k hyperbolas, just for fun. And if you left your picture exactly in this form and included the work that we see to the left, you would be good to go. But let's see one of these hyperbolas. So if I picked y, and I'm going to just randomly say 1. If we wanted to get the y equals k trace, you will have a hyperbola which opens up in the z direction, and roughly speaking, it's going to sit on our cone, and open upward and open downward. And we could do similar things for the x equals k hyperbola. It's just a bit more difficult for me to sketch those accurately. But hopefully this allows you to see where those actually sit inside our surface. So this completes the discussion of quadric surfaces and sketching using the method of tracing. And I very much realize that using this method of traces and at least showing these details as we have done here seems to be a very time-consuming process. But as you work through examples, it definitely becomes quicker. And what we're trying to do is become familiar with some of these surfaces, being able to recognize when do we have a cone, when will we have an ellipsoid, or when will we have a cylinder. And this is something that we will practice frequently as we move forward. So I highly recommend working through examples. If you have questions, feel free to reach out to me, drop an email, stop by virtual office hours. Otherwise, stay tuned and take care.